Good afternoon. Welcome to the next video in the Let's Calc series. This video we're going to focus on the mean value theorem, a theorem which allows you to draw some conclusions based on the instantaneous and average rates of change of a function, respectively, over a closed interval. It's the last in the triumvirate of value theorems that we've talked about. It kind of completes the trifecta. So we'll talk about it a little bit. We'll do some examples, some stuff involving numeric situations, some graphing calculator ones, a graphical one to start things off. We'll do the basics, and then we'll even talk about probably contrived, but still an application of the situation that you might be able to use yourself should you ever find yourself tracking speeders in a helicopter. So in any event, let's get started with our first problem that we're going to attack. Alrighty, so the first problem we're going to attack, after I close the advertisement, is we're going to look at a problem from the first section of the assignment, which is the graphical technique. So where you're trying to visually represent what the mean value theorem itself does. So in this case, it tells us in the instructions, and this is 1D by the way, this isn't 1A, this is 1D. I tried to pick kind of one that was interesting. So in 1D, it says for each graph on the half sheet, sketch the secant line for each indicated interval. So the interval is indicated by the two endpoints that we see placed. So for instance, what I notice right here is that I've got, I'm going to try to draw this. I'm trying to draw my line. There we go, close enough. So what we've got, I'm going to blow it up here really fast. Let's make this a little bit larger. Let's make this a little more thick. Okay, that might be, no, we'll let it go. We'll let it slide. So there is our secant line. So we've just sketched exactly what it said. We wanted to sketch the secant line for the indicated interval. Let me remind you here for a second that secant, for our purpose, is describing, or has the slope of the average rate of change, at least on that particular interval. So we're starting with that. The secant line represents the average rate of change itself. Then from here, it tells us to sketch any parallel tangent lines to f of x on that interval. So to do that, I'm going to take advantage of my beautifully drawn secant line. Actual beauty may vary. Always does. So I'm going to take that, and I'm supposed to place it or find the parallel tangent line. So in other words, where on the graph on that interval, or where on the graph would the parallel tangent line fall? So looking at my picture, I'm going to see one that looks like it falls somewhere right over here. And again, this isn't perfect, but it looks to me like we have a spot somewhere here in this ballpark. So I'm trying to draw a line right there. Maybe I'll move my little tangent line up a little bit. So there's one such spot. And so we just found it. And then of course it also adds to that. So if I can get the colors right here. So we sketched parallel tangent lines. I mean, I literally just lifted it up. And then we're supposed to approximate the x values that satisfy the mean value theorem. So we're supposed to say what that x value is right about there. And I don't know, I mean, if we're trying to approximate just with like halves and stuff, I might say that that's negative 1.5. I mean, here it looks a little bit like negative 1.75 or negative 1.8. But again, we're just approximating. So there's our approximate solution to the value, because it's the x value where the tangent line is parallel, aka has the same slope as the secant line. And the thought here is that if the secant line slope is the average rate of change, the tangent line slope is the instantaneous rate of change. And of course the word instantaneous has 50 trillion syllables, which means it takes forever to write. But the thought process there is that this is equal to f prime of c. And so what we end up doing here is when we try to find the x value that satisfies this, that has the same slope, what we're really solving is a particular equation. We're solving always the same equation. Assuming that we can apply it, which we'll talk about later on, we're solving f of b minus f of a over b minus a is equal to f prime of c. And we're trying to find the c value that happens to fall in the interval. Now with that said, it might be worth pointing out to you for a second that there's something a little weird here, is I drew one particular parallel tangent line, but you might wonder why it is I did not draw a second one. Actually, I'm going to cheat here. Didn't like that. That was the wrong color. Might be wondering why I didn't draw a parallel tangent line right over here, because it looks to me like there might be a second point right off here. And the reason, of course, is that we're looking for any parallel tangent lines on the interval. So over here, this one is not going to apply because our interval was from, it looks like, -4 to 1. So in other words, we were specified and stuck on the interval from -4 to 1, and the places where the potential tangent lines might be parallel that we're looking for would be on the open interval from -4 to 1. So basically we don't include that one because it's not in the interval. So with that in mind, I'm hoping that's enough for you to be able to work your way through the rest of the problems. We also did a few of them, I believe, during class. So in any event, there is a nice example from that first section where you're just sketching secant lines and then trying to place those parallel tangent lines so you can approximate a solution to what we know of as more or less, I'll put it in quotes because it's not the complete thing, but more or less the mean value theorem. Okay, next, that brings us to section 2, where we're still not solving and finding those x values using the mean value theorem. In section 2, we're looking to establish whether or not we understand when we can apply the mean value theorem. And that's a really important piece of any one of those value theorems that we have. And if you'll remember, with the intermediate value theorem and the extreme value theorem, we're required to have a continuous function on a closed interval. Here we also are required to have a continuous function on a closed interval, but there's extra requirements in there as well. So it's worth pointing out first, before we start anything here and start looking at 2D, what it is that the mean value theorem says. It says if f is continuous on the closed interval a to b, and continuity requires the closed interval, so in other words the endpoints have to be there. You can't have anything missing in the middle either. Everything has to have the limit equal the function value, and differentiable, so there's also slope requirements obviously, and differentiable on the open interval. So in other words, it's okay if our endpoints are non-differentiable. Kind of weird, but you'll eventually run into an example like that somewhere. If f is continuous on the closed interval and differentiable on the open interval, then there exists, so again this is an existence proof, or theorem, then there exists a C in a to b such that, and we say that the derivative f prime of c is equal to the secant line slope, also known as the average rate of change. So again, it doesn't tell us what it is. In order for us to do that, we have to be able to solve this equation, but it tells us that there is one that exists, and it requires continuity on the closed interval and differentiability on the open. So with that in mind, in each question from section number 2, you're looking to see which property it is that this thing violates. Is it not continuous on the interval? Is it not differentiable? There's something else going on. So in this example, an f of x equals this piecewise function. Our job is to figure out why the mean value theorem can't be applied, specifically on the interval from -3 to 5. Now a couple things to point out first is each branch, -2x plus 4 and x squared plus 1, are polynomials. And the reason I bring that up is that being a polynomial means that you're instantly eligible for the mean value theorem. In fact, you're instantly eligible as a polynomial for all 3 of the value theorems. And the reason is all polynomials are continuous and differentiable everywhere. So what this tells us in our particular problem here is that there is no x value on either one's pieces or on either branch where there is any sort of discontinuity or differentiability problem. So that means the only place that we need to look is the boundary. So what we need to do here in order to find if this is actually differentiable is we need to consider the boundary, which in our case is at x equals 1. Now first, it's worth pointing out that x equals 1 is a member of that interval from -3 to 5, so that means we could have a problem there. Otherwise, we'd be done. We'd be set. Everything would be good to go. So in order to check the boundary, we're going to check 2 things, just as always. First, we're going to check if it's continuous there, because if there's a jump, then obviously this isn't going to apply anyway. So first, we check for continuity. So in order to check for continuity, of course, we know there's a 3-step proof to get there, with the function value, the limit, and the 2 being equal. I'm going to focus on the second step, which talks about the left-hand and right-hand limits. So we're going to ask ourselves, does the limit as x approaches 1 from the left side of f of x equal the limit as x approaches 1 from the right side of f of x? So in a sense, it's like a question here. So looking at our ingredients, if we're plugging in 1, on the left, we're going to have -2 times 1 plus 4. On the other side, we're going to have 1 squared plus 1. That gets us -2 plus 4 is 2, and 2. They both equal one another, so it sounds like this function is in fact continuous. So that's not going to disqualify us at all. It's almost like the first step is satisfied. That means our only potential issue could be with differentiability. So let's go check the differentiability really fast. So let's go differentiable. And again, I'm just writing diffable because, I don't know, I'm lazy. So from here, what we want to check is the left-hand limit of the derivative and whether or not it's equal to the right-hand limit of the derivative. So we're questioning that fact. So in here, it's worth pointing out, we didn't calculate it earlier, f prime of x is not difficult to find. F prime of x is going to be -2 when x is less than 1, and it's going to be just 2x when x is greater than 1, with the ability to have an or equal to sign determined based on our work here. So with that in mind, if x is less than 1, the slope is clearly -2. If x is greater than 1, our slope is 2 times 1, which means that we get -2 equals 2. Unfortunately, that is not true. And what that tells us is that we have just discovered that because the function is continuous at x equals 1, but not differentiable, or the slopes don't match, that means that we have a sharp turn at x equals 1, which implies that f is not differentiable on -3 to 5. And of course, the reason that's important is the mean value theorem doesn't apply. So we had to have, according to the statement, we had to have f be differentiable on the open interval. We found it wasn't at x equals 1. That discludes it, which means that we have our answer, that f is not differentiable due to the sharp turn that occurs at 1. So again, this is way more involved than the average problem. Typically, you can recognize your favorite non-differentiable functions. You'll recognize the vertical asymptote presence. You'll recognize a hole. You'll recognize when there's an absolute value and there's a sharp turn there, or a vertical tangent on a cube root or an odd root of some kind. In this case, we had a piecewise, so we had to do a little bit more work, but everything came out clean when we did. Okay, finally, we get to the section that asks us to actually solve. So up to this point, it's just been like satisfying the mean value theorem. Now we're ready to actually look at what's here. So in question 3, which involves, I think, 5 parts, we're asked to first verify that the mean value theorem can be applied to f on the indicated interval. If it can, find the x value guaranteed by the MVT. So in here, before we start anything else, that first statement, or that first request, tells us that we need to verify the mean value theorem applies. So in our case, we start here by recognizing that our function in 3b is 3x cubed minus x. That means f is a polynomial, and that means, of course, that f is continuous and differentiable. So the first statement that we needed, or the first qualification we had for a function, was continuity and differentiability on that interval. Well, since f's a polynomial, it's continuous and differentiable everywhere. So good job us, we've got it. So the mean value theorem applies in this case. Our next step is we're going to focus on the average rate of change. So next we want to figure out what is f of 3 minus f of -1, and I'm choosing those x values because those are the intervals that they provided us, all divided by 3 minus a -1. So from here, if we plug in, we're going to get 3 times 27 is 81 minus 3. And then minus, if we plug in -1, we'll have -3 minus a -1. All of this will be over 3 plus 1 is 4. Cleaning up, we get 78 minus a -2 over 4, which is 80 over 2, or 80 over 4, which is 20. So we found our average rate of change. That's half the battle, or more likely a third of the battle, maybe 2/5 of the battle, I don't know. So we found our average rate of change in the interval. That was the first piece that we needed. Next, we need to compute the derivative, because again, our goal is to figure out where the average rate of change, or the slope of the secant line, is equivalent to the slope of the tangent line, so that those two lines will be parallel. They'll be equivalent in their slope. So to find f prime of x, we just got a polynomial. I'm just going to take the derivative with respect to x of 3x cubed minus x. When we do, we get 9x squared minus 1. So with those two pieces in place, our next task is to actually get to the full problem solving. Average rate of change, derivative. We want the average rate of change to equal the derivative. And if that's true, that's going to give us the equation 20 equals 9x squared minus 1. So this is our task to solve. So solving some things around, we're going to get that 21 over 9 equals x squared. It's going to tell us that x is equal to plus or minus the square root. I think that's 7 over 3. And of course, rationalization is allowed. So at this point, you're tempted to go, yeah, and just finish the problem because you found your x value. We found a place where the slope of the tangent line matches the slope of the secant line. But there is one more piece in here that's very easy to forget and lose track of. I'm going to go back, in fact, for a second to take a look. It says then there is a c in the open interval from a to b. So specifically, we need to find the value that's in the interval we're looking at. And in our particular problem, we want to be in the interval from -1 to 3. So to make that determination isn't trivial. Can't lie to you. Tried really hard to make this problem work out easier than this, but I could not make it work that way with any cubics. So this is basically where we're stuck. So our question to ask ourselves is, which of these two values actually falls in -1 to 3? So to answer that question, here's what I did. And again, this is my clever way. Of course, you could reach for a calculator on a non-calculator question. You might call that cheating, but I mean, I get it. But in this case, here's my thought. So first, 7 over 3 is equivalent to 2 1/3, right? Right, that's true. Exactly. So from here then, the next question is, well, what's the size of the square root of 2 1/3? Well, we know the square root of 1 equals 1 is 1. And we know the square root of 4 is 2. That means the square root of 2 1/3 is going to be between 1 and 2. So with that in mind, that means a couple different things. That means that the square root, as we said, of 7 over 3 is in 1 to 2, which means that it qualifies. That's a good thing. That's definitely between -1 and 3. But that means that the negative square root of 7 over 3 is between -2 and -1. Now that is not inside our interval, which means that our answer is that x is only equal to the positive square root of 7 over 3. So typically, just to kind of illustrate, you might even say this is me showing off that I know to apply the mean value theorem correctly. I'll write that this is true for square root of 7 over 3 only. And again, there's lots of different ways to get here. If we had a calculator, this would be trivial. But of course, this is a non-calculator question, so your approach had to be a little bit different. But interestingly enough, I feel like this is a very basic problem up until that end when you're making the determination. But there's one strategy you could take to determine that very thing. Okay, next, that brings us to question 3e. And 3e is kind of the plus question of this technique. In fact, the only time I'd ever asked a question at this level was either on a challenge question or on the plus test that I wrote back in 2016. So let's take a look at it for a second. So again, we're trying to verify that the mean value theorem can be applied. If it can, we want to find the x value guaranteed by the mean value theorem. So interestingly enough, because we have a piecewise function, we really can't do anything. We can't even attempt the mean value theorem until we know for sure that this function even works on the interval it's established here, which is going from -1 to 2. So to start things off, I'm going to actually begin in kind of an interesting place. I'm going to first check if this function is continuous. And in looking here, again, I'm not going to write everything out as much as I probably should, but in looking here, I notice that each branch is a polynomial. So I know the two branches are inherently continuous and differentiable automatically. So really, it's all interesting. It's all up to us to determine if this is continuous at x equals 0, the boundary point. So in grand fashion, we're going to take the limit as x approaches 0 from the left of f of x, and we're going to check if it's equal to the limit as x approaches x approaches 0 from the right of f of x. So again, we're asking the question. So I'm plugging in down here. If we plug in 0, we get 6 times 0 minus 0 squared. And on the other side, we get 0 cubed plus 6 times 0. Oh, that was easy. Okay, so that gives us 0 and 0, which are equal. So yes, this is a continuous function. So good job, we determined that portion. At least we know it's continuous. Next, we're going to check if the function is differentiable at x equals 0. So from there, almost like I'm going to put like a semicolon. Next, we've got, is it differentiable? It's the other question we have to answer. And again, you can kind of see what makes this challenging is we're just even getting into the problem takes a little bit of work for us to start to determine the answer to this question. So now it'd be helpful if we began by having defined for us f prime of x. So let's do that really quickly. So looking up there, the derivative will be 6 minus 2x when x is less than 0, and then 3x squared plus 6 when x is greater than 0, with again the or equal to determined still to be determined. So we're going to do the exacts. You know what? I'm going to be that guy. I know you guys can't do this on your assignment. It's too bad. I wish you could. If only the world were fair. I'm going to literally do this. Never saw it coming. Ha ha ha. So we're going to check to determine if this is differentiable by looking at the limit as x approaches 0 of f prime of x from the left and from the right. So when we approach 0 from the left, we're going to be plugging into 6 minus 2 times 0. And if we go from the right, we're going to get 3 times 0 squared plus 6. This gets me 6 minus 0 and 0 plus 6, which means those two are equal. So the answer is yes. So that tells us that the mean value theorem applies. So that was a lot of work to get our foot in the door, but now that we have it, we're eligible to continue. And again, this is as good a time as any to remind you, this is a challenging question. This is a hard application. This is tough. So now, with that said, we got to do the normal calculation. So we're going to do f of 2 minus f of negative 1 all over 2 minus a negative 1. So I'm looking here, f of 2 is bigger than 0, so we're going to plug it in. It's going to give us 2 cubed plus 6 times 2. And then f of negative 1, since negative 1 is less than 0, it's going to be 6 times negative 1 minus negative 1 squared. And all of that is going to be divided by 3. Simplifying here, we get 8 plus 12. Is that right? 8 plus 12 is 20. On the other hand, we're going to get minus 6 minus 1 is minus 7. So it's 20 minus a negative 7 all over 3, which is 27 over 3, or 9. So our average rate of change is 9. Likewise, the other piece that we need is the derivative itself. We need to know what f prime of x is, and we already calculated that. We have it right up there. So our question really is, if we think about this, we don't need to even write it again. We already calculated out what f prime is. So what we need to answer for ourselves here is when does 9 equal the derivative? So of course, if you want to check that, if we want to check when does f prime of x equal 9, that means that we need to check two separate possibilities. 9 could be equal to 6 minus 2x, or 9 could be equal to 3x squared plus 6. So let's solve both those equations and see what happens. First one, we get 2x equals negative 3, or x equals negative 3 over 2. We'll play with that in a second. On this side, we're going to get that 3 equals 3x squared, or x squared equals 1, which gives us x equals minus 1 or positive 1. So it looks like we found three values. Yay, yes! Except, of course, remember our interval. And this is actually one of those challenging places. I kind of teased it earlier, in fact. I said that what we're guaranteed, we'll go back a little bit, is we're guaranteed a c on the open interval. So we're looking for which of these values are on the open interval from negative 1 to 2. In looking here at our values, negative 3 halves is negative 1.5. Negative 3 halves is out. So it's not included there. And weird as it is, negative 1 is also out. It's in the open or in the closed interval, but we're looking for values in the open interval. Those are the ones that are guaranteed by the MVT. So that means the only one that works is 1, and that means our answer is x equals 1 only. So in this weird case, we've got a piecewise function that is somehow differentiable just by bringing together a parabola and a cubic. And even though one of the endpoints produces the slope that we are looking for, the only value guaranteed by the MVT is x equals 1, because it's the only one that's in the interval we were looking for. So again, this is a hard question, hard with a capital H-A-R-D. So just know this is tough, but hey, if you can work your way through this, you've really got a good command of piecewise functions as well as what's happening in this particular problem. Okay, next, that brings us to our first calculator-based question. I think the other ones that were on there were pretty basic. Really quickly, let's pull up the TI-Smartview. We're going to need that puppy in just a second. So in this case, in question 4a at least, we're given the function g of x equals the sine of x squared, and we're on the interval from 1 to 3. Now the part that I'm not going to spend a lot of time talking about is the verifying that this can be applied. If this were a test question, I would tell you automatically that g of x is differentiable and continuous. I just forgot to include it on the assignment already. But in here, the sort of theory is that sine of x is continuous and differentiable, x squared is continuous and differentiable, therefore the composition of those two should be differentiable and continuous as well. And I believe, I could be wrong, but I believe that the composition of differentiable functions are also differentiable. And since differentiability implies continuity, continuous as well. So for our purposes here, we're looking for a familiar face. We want to apply it. We're going to assume it verifies. So we'll just put that in there for now. Just acknowledge the fact that I'm not being as, firm as I could be. So we assume the mean value theorem applies. So what do we want? We want g of 3 minus g of 1 over 3 minus 1 to be equal to g prime of x. Well, let's calculate out the two different values. So g of 3, that's going to be the sine of 3 squared minus the sine of 1 squared. And that's all over 2. So in other words, the average rate of change is sine of 9 minus sine of 1 all over 2. And if you're spending time looking at this going, that's not fun. Yeah, you're right, it's not. But again, keep in mind, this is a calculator question. We're going to have a tool that can work with, values that we don't have exact ones for. So just know that that's there. Likewise, we want the derivative of this function so that we can eventually set those two things equal to on the calculator. In our function here, if g of x, why did I choose red? Wow, that's one of the most colorblind things I've ever done. Excuse me. Okay, so if g of x equals sine of x squared, which it tells us it is, then we can, of course, use the chain rule because we've got x squared inside of the sine. And we even talked about composition a few seconds ago. So because we're still early in the unit, we could decompose this into sine of u with u equal to x squared. G prime of u would be cosine of u prime would be 2x, and then I'm going to trust that you're comfortable with the fact that our derivative would be 2x cosine of x squared. So in other words, what we're trying to solve here is when does sine of 9 minus sine of 1 over 2 equal 2x cosine of x squared. Now, if you were one of those, determined to do it yourself, excuse me, without a calculator persons, this would be a miserable opportunity to point out that you really don't have that much power. You're really limited in the things you can do. Not just because you're you, or because you're just learning calculus, but because it's really hard. There's just a lot of techniques that just aren't out there algebraically. So in fact, all we can do at this point is use this as an opportunity to pull our graphing calculator into the world here. So what we're going to do is we're going to graph each of these two, and we're going to find their intersection. So in fact, what I'm going to do is I'm going to put into my calculator y1 as sine of 9 minus sine of 1 over 2, and I put it in as y2, 2x cosine of x squared. And now I have to find somewhere to put the calculator. Continue the trial version. Find somewhere that does not hide everything. So what happens here? Close enough. We'll make it work. Here, I'm going to shrink this really fast. Things you don't have to worry about when you're not making a video with a calculator. Boom. Let's make this a little bit smaller as well. Boom. Okay. So we're looking at our calculator here. Let's punch this in. So I want to put in the average rate of change first. I'm going to go into the fraction button. Otherwise, you just have to use parentheses carefully. I'm going to put it as my numerator as sine of 9 minus sine of 1. And all of that is over 3 minus 1, also known as 2. Second, I'm going to put in the derivative itself, 2x times cosine of x squared. So we have y1 and y2 as the two things we want. We're going to look for the intersection of those two pieces. Now it's tempting to just go zoom 6 and just kind of go, oh my gosh, there's a billion values. And just kind of go, well, ain't nobody got time for that. And just stop. The thing is, remember what we were told in the problem. We were told to find all the values between 1 and 3, inclusive or exclusive. So in other words, our picture on our calculator isn't accurate. So I'm going to change the window here. I want to change my window. I want it to run from 1 to 3. And then because I saw that average rate of change was really small, close to 0 it looked like, I'm going to go from negative, 2 to 2. It's just this guess. I could be wrong, but there it is. Nope, that's pretty good. Okay, so now what I see that there are 3 places here that are crossing. In fact, let me just steal this really fast and punch it into our piece. So we've got that. There's our thing that we need to find the intersections for. Now it's just a matter of finding the intersections. Each one, I'm going to go to second trace. I'll do option 5, enter, enter, and then the first one is close to 1. So my first one is 1.286. The second one, and again, there's no way to fast do this without actually just cheating and giving you the values. You'll notice that I'm taking advantage here by choosing the x value so I can get close to it, 2.159. Remember, each of these values should definitely be between 1 and 3, simply because those are the ones we were looking for. And if this one, we'll go enter, enter, and then we'll go closer to 3. 2.809. So there are the 3 values. And just as kind of a reminder, like those are the values we were looking for. They're the ones guaranteed by the mean value theorem. Remember, what this tells us is they're saying that the slope should be equal to our average rate of change at those points. Well, if we plug in one of them, and in fact, I'm going to choose the last one, which was right now is stored as x. There's 2.809. I'm going to store x as a for simplicity. And then I want to see what the derivative is at this particular point and make sure that it's actually equal to, what do we have? Sine of 9 minus sine of 1 divided by 2. So that's the slope we're looking for. So if I go to Math 8, I say we're going to go from x, we're going to use sine of x squared as our function. We want to evaluate it at x equals a. This should give us the negative 0.214 thing. And notice, in fact, it does. Like the decimals are off at the end, but we have an accurate answer. Just know it's because it's difficult for the calculator to maintain that kind of accuracy. So in any event, though, we found our values. All we need to do is use the graphing calculator because we weren't able to solve that equation by hand. So there it is. There's one. You get to do the other one completely on your own, or look at the written solutions. But so voila. Okay, that brings us to question number 5. And now I will tell you a fun story, actual fun may vary, about question number 5. I spent a lot longer than I probably should have trying to come up with a function that would give me nice numbers, and then eventually I just completely gave up on the problem and went, I don't care, and I just put the number 17 into it. Well, something nice happened. So here we go. So it says in question number 5, for a differentiable function f, it is known that f prime of x equals the square root of x cubed plus 17. So they're giving us the derivative here. So that's kind of an interesting twist. Normally we have to find that. We did not in this particular case. Second, it says if f of 5 minus f of 3 is 18, find the x values guaranteed by the mean value theorem for 3 to 5. So a couple things. It tells us that f is differentiable. So if f is differentiable, the first thing we know is that f being differentiable implies f is continuous also. Differentiability implies continuity. So that tells us that the mean value theorem applies, specifically to f. So that's an important place to start. Excuse me. It's an important place to begin. Next from there, let's remember what the mean value theorem guarantees. It says that f prime of x is going to equal f of b minus f of a over b minus a at some value x in the interval. Well, in this particular case, let's just kind of look at what we know. We know f prime of x. In fact, here I'll use colors. Getting better at using color here. We know f prime of x, specifically. There's f prime of x, so that means the square root of x cubed plus 17 is going to be equal to f of, let's see, our interval is 3 to 5, so f of 5 minus f of 3 over 5 minus 3. So we're asked to find that. Well, unfortunately, we don't seem to know enough information here because we don't know what f is. We don't have any way to undo differentiation. But hold on a second. They tell us f of 5 minus f of 3 is 18. That means down here, we can ignore f of 5 minus f of 3 and just point out that's the same thing as 18. So now we have the derivative with an x in it is equal to 18 over 5 minus 3. That's equal to 18 over 2, or 9. So what we're really trying to do is solve the equation square root of x cubed plus 17 equals 9. And that's just an algebra 2 kind of problem, or a math 2, math 3 kind of question. So from there, I'm just going to solve the equation. We'll get x cubed plus 17 equals 81. From there, we will subtract 17 from both sides. Look at me being good here, just because I'm so proud of how this turned out. 81 minus 17, anybody? 64. What number to the third power gives you 64? That would be x equals 4, which is definitely in the interval from 3 to 5. In fact, it's at the midpoint of the interval. So with that said, there's our value. This is one of those questions where the work that you're doing isn't very difficult. It's actually a pretty low-level mathematical task, but it's the trust in bringing the information together, and it's one that I like to call especially efficient, where you're given an efficient and limited amount of information, but it's the exact right information that you need. It's like going on one of those cooking shows, and they tell you have to come up with the thing, you have to come up with the thing from scratch, but they've given you the exact amount of flour that you need to bake the cupcakes. You don't have to worry about it because they gave you the right amount. That takes something off the plate, and that's what happens in question number 5. Okay, finally, that gets us to, or not finally, I think there's one question after. That brings us to question number 6. Question number 6 is the multi-part free response style question that involves a table of values. In this case, I believe I'm doing A, C, and D. I'm not doing B because B and A are identical. So I just want to talk about the values here, or the approach here. So in our statement of 6, it says let functions f and g be twice differentiable functions. Sorted values of both functions and their derivatives are given in the table below. Use the table to answer the questions. So our table's off to that side. I don't know, it's hard to go backwards. In question 6a specifically, we're asked to find the x value guaranteed by the mean value theorem for f of x on the interval from -3 to 6. So from -3 to 6, there's a bunch of different things to go through. First thing I want to point out is we're talking about function f, and it tells us that f is twice differentiable. So because there's really no other opportunity to bring this up, question you might ask is, well, does twice differentiable mean that we get everything we need for the mean value theorem? Well, what that tells us is this. First, if f is twice differentiable, that means that f double prime is, that means that f double prime is continuous. So that would be kind of the definition of twice differentiable. But remember, those are other things that come with that. If f double prime is continuous, that means, because differentiability implies continuity, that f prime, the function whose derivative is f double prime, is continuous as well. Well, if f prime is continuous, that is the definition of f being differentiable. Its derivative is continuous. And then finally, you can see how fun this is, this mathematical reasoning. If f is differentiable, differentiability implies continuity, which means f is continuous. So given those last two statements here, that's enough for us to say that the mean value theorem applies, specifically here to f of x, although it would also apply obviously to g because of the same properties. So with that out of the way, there's your one explanation, the one time we're going to go through all that in depth and be able to say that this makes f applicable for the mean value theorem. Otherwise, that means we need to figure out the statement. So in our case, we're looking on the interval from -3 to 6. So we want f of 6 minus f of -3, all divided by 6 minus -3. So in this case, we'll just find those values now. F of 6 is 5, minus f of -3, which is 23, all over 6 plus 3. That's going to be -18 over 9 equals -2. So we just found the average rate of change. Remember, though, what the mean value theorem says is, given continuity and differentiability in appropriate ways, then the average rate of change is going to be equal to the derivative at some x value c. So we want to figure out what is that x value. So in other words, what we're trying to solve from here is we're trying to figure out when does -2 equal f prime of c for some c value on the interval from -3 to 6. And gosh darn it, we don't even know what f is. We only know some values, and we only know some values of the derivative. Like, the question might be, is this even possible? And it certainly might not be possible unless the table has been constructed appropriately. So if we're trying to solve this equation, we're looking for a value x where f prime equals negative, oh, look at that. f prime of x equals negative 2 at x equals 2. Is 2 between negative 3 and 6? It is. So x, or f prime of 2 equals negative 2, which implies the value we want is x equals 2. And there is our value. So in a sense, some people might call this like a little scavenger hunt. It's trying to match some different pieces out of the table. But in reality, what you're doing is you're solving the same equation you have all this whole time. Average rate of change equals instantaneous rate of change. You're just using a table of values to do it numerically. Okay, that next brings us to question 6c. Again, I chose to skip 6b intentionally just because it's the same as 6a. 6c, though, is a very interesting question. It was inspired by an old free response question, and this one I've made kind of interesting. So in question 6c, you are asked, is there a number c in the interval from 2 to 6 such that f prime of c equals 5/4? And your job is to justify your answer. And I'm going to tell you right now that there are actually two completely different but both equally valid approaches that you could take to this question. In the written solutions, I only did one, but depending on what catches your eye, you might actually decide to go through a different one. So the first one I'm going to point out is what I would call like the intentional one, the one that's designed here. Like, think about the problem set we're working on. It's focused on the mean value theorem. There must be something involving the mean value theorem. So in here, the first thing to deal with is if we're thinking MVT, so that's our approach, the first thing to think about is about differentiability and continuity. So to start, we're talking about f. So f is twice differentiable. So thus, f is both differentiable and continuous. And remember, we already talked about specifically why that's true. We did the entire thing like a problem back, but for now it's good to know that. So that means that the mean value theorem applies here. Second, we need to consider that interval. So here's the thought. If you see this and you're in a mean value theorem problem set, you're thinking this must be the right interval to get a particular average rate of change. So let's see. What is f of 6 minus f of 2 over 6 minus 2 equal to? Looking at our table, f of 6 is 5, minus f of 2 is 0, all over 6 minus 2, which is 4, which means that the average rate of change is equal to 5/4. So that's told us now, let's see. We've now shown that the function in question f is both differentiable and continuous. We've shown that the average rate of change is 5/4. So therefore, what do you call it? And I guess we could go fast with this thing. If I was going to state it more formally, if I wanted to restate this formally, or I want to do it without having to show all this extra work, I'll write this in one better step. I'd say because f is twice differentiable, f is both differentiable and continuous. And since f of 6 minus f of 2 over 6 minus 2 equals 5/4, thus f prime of c equals 5/4 for some c in 2 to 6 by the mean value theorem. So again, that moved really fast, but taking a step back for just a second here to kind of re-explain what we were doing. Again, this was kind of speculative. This was taking context into account and realizing, hey, this is the problem set we're on. This must be what we're doing. They asked us about whether there was a particular number in the interval from 2 to 6 where f prime of c equals 5/4. Our job was then to verify that the mean value theorem applied by explicitly mentioning differentiability and continuity and where they came from. Second, calculating out the average rate of change via the difference quotient. And then stating the mean value theorems, invoking it and using it appropriately. So in other words, saying that the derivative must be equal to the average rate of change for that value, some value in that interval. And again, that is the mean value theorem approach to this particular problem. This is what I would call the intended approach. This is what I wanted you to do when I wrote the question. But keep in mind, of course, sometimes there are alternate approaches. And there's no single approach that's going to get you the wrong answer if it's done correctly. So our second approach here, which is not the one that I think would be the intended one, but one is completely valid, is to use a different value theorem. So let's focus in for a second on f prime of x on the interval from 2 to 6. So here is f prime of x on 2 to 6. So I noticed that going from -2 to 4, 5/4 is in the middle. So basically this is my notice, that if we're going from -2 to 4, 5/4 falls in the middle there. So this makes me think of the intermediate value theorem. If we could just guarantee that it was in there and we had a continuous function, we could guarantee it. So here's my thought here. We could also use an IVT approach. And this actually came up, I think, on a question from 2018, if memory serves, on a free response question, where you had options. So for the IVT, f is twice differentiable. So f prime is continuous. And again, if you want to follow all those pieces, you could go through and say f is differentiable, and then therefore f prime is continuous. And since those values were given in the table, we can see that f prime of 2 is less than 5/4 is less than f prime of 6. Therefore, by the intermediate value theorem, I don't want to write the word intermediate value theorem, but here I am. If I just complain the entire time, it makes it go faster. Intermediate value theorem. There we go. So therefore, by the intermediate value theorem, f prime of c equals 5/4 for sum 2 less than c less than 6. So notice that one accomplishes exactly the same thing. We were able to guarantee there was a place where the derivative equaled 5/4, or f's derivative equaled 5/4. Difference was here we took advantage of the continuity of f prime given by twice differentiability to use the intermediate value theorem. So again, both approaches 100% accurate and valid. It's just up to you which one you choose. I chose the first one because I felt like that was the focal point of the assignment, but I would accept both on an exam. So there you go. Tough AP style question, but a great one to really test your ability to invoke and use and properly justify using the mean value theorem. Okay, question number 6. Another new favorite of mine, one that was written yesterday or last night. So it says in 6D, for x greater than or equal to 11, which looking at our table we don't have anything established for, it is known that 3 is less than or equal to f prime of x is less than or equal to 9. So in other words, the derivative of f is between 3 and 9. That's something that we know is true. So x greater than or equal to 11 implies f prime of x is a member of the interval from 3 to 9. And actually, I'd rather write it as an inequality, even though it's already up there. 3 less than or equal to f prime of x less than or equal to 9. So they're saying that the slope is positive and always between positive 3 and positive 9 on that interval. The question we're asking is whether it's possible that f of 15 equals 54. And in your head, you might just feel like this is one of those questions where there's just not enough information. There's so little given. You'd know so little about what's happening with f beyond x equals 11, so you might feel like this can't be done. But actually it can. So let's take a look and think about some things. So we've said this a million times already, but f is twice differentiable. And again, I'm stating this each time just to be super careful because you don't know which of these question types might pop up somewhere. So f is continuous and differentiable. So we get both those pieces. Nice to know. So that means mean value theorem applies, by the way. So MVT applies. Good, good, good. The next thing. Well, we're talking about f of 15. So if we're talking about f of 15 and we're in the context of slope and the mean value theorem, here's my thought. The only thing we can do with that f of 15 is set up an average rate of change, right? Let's just do that, because then what else are we going to do with it? We don't know enough information otherwise. So let's see. F of 15 minus f of 11, and we'll use 11 because we're talking about that interval, over 15 minus 11 has to be equal to f prime of c for some c between 11 and 15. Right? That is by the mean value theorem. That's just what the MVT says. Okay, and again, this is all kind of speculative. I'm just kind of pulling things together, but there's my thought. So we have a continuous and differentiable function. That means the average rate of change is equal to the derivative for some x value between 11 and 15. So let's go with that. So let's see. F of 15, they told us that's 54. We're considering the possibility. F of 11 tells us right there is 2. And this is all over 4. So that means 52 over 4, which comes like the number of cards in each type. That's 13. So what we just found is that the average rate of change is 13 on that interval if f of 15 is 54. And by the mean value theorem, 13 has to equal f prime of c for some c value between 11 and 15. But no, that's not possible. We've arrived at what we'd call mathematically a contradiction. We said if x is greater than 11, then f prime is between 3 and 9. But c is greater than 11, so f prime of c is between, or so, there we go, go this way, because, so that means 3 is less than or equal to f prime of c is less than or equal to 9. Thus, this is impossible. So in other words, what we've shown is that if f of 15 is equal to 54, then the average rate of change is larger than 9, which guarantees a slope that's larger than the 9, which we know from what we were told is impossible. Thus, this is impossible. So f of 15 cannot be 54. We've done this using what we would call proof by contradiction, in fact. So this is a fantastic question. This is the sort of thing that really pushes your thinking forward a little bit. It uses the concept of boundedness in a really unique way. And again, it's one of those things where it's very efficiently written. You're only given so much information here. We're on a problem set about the mean value theorem. This would be your attack strategy. And there it is. Everything's in place. We did a really nice job. And finally, this brings us to the last question here. This is a word problem. These aren't my favorite questions to ask because they're kind of tough to explain. But I think it's a nice opportunity to see how theoretically you could apply the mean value theorem out in the world at large, like the sort of things you might want to do. So in our situation, we'll read the story once. Jaime, this is based on, I think he just graduated. Maybe he's graduating this year. Jaime Campos, like his brother Joel, is at Franklin still. So Jaime goes on a ride-along with the Elk Grove police and ends up flying with the helicopter patrol. Not sure if we have one of those, but for the sake of fiction, we do. While in the air, he watches a car drive down the 2.2-mile stretch of Whitelock Parkway between Franklin and Cosumnes Oaks without stopping, so it must have hit some lights or ran some lights, in exactly 2 minutes. So 2 minutes to go 2.2 miles. Jaime suggests they radio down to pull the car over for speeding, but the officer says they can't give a ticket without proof that the car's driver exceeded the 40-mile-per-hour speed limit on Whitelock Parkway. Jaime, though, says that he can prove it with calculus. Your job would be to explain Jaime's argument here. So there's a lot of stuff that's kind of built in here, and again, knowing which problem set, I didn't even realize I could do this, knowing which problem set we're talking about really helps you in a sense. Like, we've got to be talking about the mean value theorem. But that's exactly what we want to do here. We want to see how Jaime can use the information about how far it traveled and in what time to somehow guarantee that the speed exceeded 40 miles per hour. So let's think about a couple different things. So first of all, we're interested in talking about the car's speed or velocity. And in this case, it's just going in one direction. So we're only worried about that. So we are going to assume, in fact, I should write this down here. This is an assumption. We have to make this assumption. We are going to assume that the car's speed or velocity is continuous and differentiable. And it's a little hard. Continuous, I think, makes a lot of sense. Like, it's always going to be smooth. It's a little bit harder to confirm that it's differentiable here. But keep in mind that if the speed and velocity of the car was not continuous and differentiable, that would mean its position was not continuous, potentially, or differentiable. Which would be bad, because if its position isn't continuous, that would mean it could just teleport. And if this car's teleporting down Whitelock Parkway, we have bigger fish to fry than just worrying about speeding ticket. So keep in mind, I am making that an assumption. Like I said, assume. So write the word assumption, because that's a fun word to actually say and write. Assumption. Our assumption is that this holds. If this doesn't hold, then again, bigger fish to fry. We've got more things to worry about. So keeping that in mind. So if that's true, if the speed and velocity is continuous and differentiable, then that would imply that the mean value theorem applies to it. So that would mean or sorry, that would imply from there that the position is, what do you call it? What am I trying to do here? Oh, shoot. Okay, gotcha. I started this wrong. I'm just going to start this problem again. No, I'm just going to do it right now. Who cares? So we're assuming that the car's speed and velocity is continuous. If that's true, because of the fact that velocity is the derivative of position, that implies that the position is continuous and differentiable. It's hard to read. Continuous and differentiable, excuse me. So that's our assumption. The position is continuous and differentiable. Therefore, if we let the car's position, so we'll let P of t equal car's position, and we'll let V of t, terrible t, we'll let V of t equal the car's rate of change. We'll call it the velocity, even though speed would be just as appropriate here. Then what we're told is, since the position is continuous and differentiable, the mean value theorem applies. Right? We can use the mean value theorem in this particular context. So with that said, the mean value theorem applies, then P of B, is that lead and stuff? Whatever. P of B minus P of A over B minus A is equal to P prime of t. But remember, we said P prime of t is going to be the velocity. So this was literally P prime of t. So with that in mind, now let's think about these things. So P of B minus P of A is going to be the change in position. So P of B minus P of A equals the car's change in position. Well, that would be the distance that it traveled during that interval, or its displacement. And it tells us right in the problem that it was a 2.2 mile stretch that we watched it go. So that means the numerator is 2.2 miles. In the denominator, we have how long it took to travel. B minus A is going to be the time that was spent traveling. Now, as we look down there and start to think about it, you might start to think that, oh, that's 2 minutes. But think about our units. We want to figure out and talk about 40 mile per hour. So what I need to realize is that 2 minutes is equivalent to, let's see, 1 hour per 60 minutes. So if we do a quick little conversion here, we get that that's equal to 1/30th of an hour. So that means down below, B minus A can be written as 1 over 30 hours. And of course, this is selfish. We're trying to make it so that our units are miles per hour. Finally, bringing everything back together here, that's going to be equal to the velocity at some point t during its travel, or during its path. And 2.2 divided by 30 is equal to 66 with the units miles per hour. So what we've just shown here, and again, it's going to be easier for me to talk through it than it is to write it down here just because of space. We've shown that there was a time where the car was traveling, I'm just going to say going, the car was going 66 miles per hour. Because, of course, the mean value theorem guarantees there's a place where the average rate of change, in our case, the average speed, is equal to the instantaneous rate of change, in our case, the instantaneous speed. So we've just proven, or Jaime has just proven, that the car was going 66 miles per hour at some time, which means that the person can get a ticket, which is good for them because 66 is pretty darn fast on that road, particularly if there are people potentially walking. But it would probably be sad if it was you, but fair. So there is our outline. We use the mean value theorem to get there. So I guess the police would cite that in a court of law if they're like, wait, how did you prove it? You were watching from above. And they're like, the mean value theorem. Probably easier just to have a radar gun on it. But the fact is, this is still absolutely true. And with that actually concludes, speaking of true things, that concludes our video here focused on the mean value theorem problem set. Hopefully this has opened your eyes towards a few other ways you could use the mean value theorem rather than just that simple solving equation, shown you some interesting, difficult, kind of challenging problems involving the mean value theorem, and left you in good position on the assignment. Without further ado, thank you for watching, and have a great night.